back to episode number 28 of the Shock Show. This title is going to be kind of long. I'm going to have to edit it for the YouTube video. But what is the relationship between electrical parameters and mechanical oscillation? And I had to make a caveat to this because the lesson was getting kind of long, so I'm only limiting this discussion to off-resonance actuation. But that being said, many of these same concepts can apply to ultrasonic resonance, and at the same time, we're going to get into that probably in the next video. But at the same time, although this is only dealing with, this is not specifically dealing with ultrasonic transducers, ultrasonic transducers can be operated in off-resonance region, and you can learn things from it, from driving it in off-resonance. It's a beautiful thing, actually. So let's go ahead and go with the next slide. All right, so this is an off-resonance equivalent circuit for a piezo. It has two capacitors in parallel. It's very similar to the resonance circuit, the BVD circuit, where you have a capacitor in parallel with an LCR circuit representing obviously the mechanical resonance. So the off resonance has, you could consider it just to be one capacitor, but that doesn't really tell you much. So we're considering it to have a pure dielectric capacitor on the top. So that's only representing current due to the pure dielectric response, let's say independent of any mechanical behavior. And the second is a electromechanical current on the bottom, and that's going to be affected and going to represent current generated through mechanical motion. As you know, the ions displaced in piezos when they oscillate, whether you're putting a force on it and therefore causing that change in displacement between the positive centers of positive and negative charge, or you're actually exciting it and you're causing that movement yourself. Both of those are going to generate charge, but in the one case, for the direct piezo effect, you're going to be, that charge is going to remain on the surface, therefore it's going to generate voltage. But on the case of the actuator, you are controlling that voltage, so therefore you're going to get current back and forth from your amplifier or your driving source. So let's take a look at that fact a little bit closer, not upside down, but right side up. So the total current is equal to the I, the current subscript D, which is the dielectric current, plus the IM, which is the mechanical current. This can also be said to be true for resonance also as well. But there's going to be some phase angles involved in that case. So let's keep going. So you're always going to have, for that dielectric current, your clamped capacitance multiplied by your omega here, which is the velocity, multiplied by your voltage. That's as simple as that. It's just a capacitor. And the next part here is the mechanical current. This is the interesting stuff. This is how you can use your current for your piezoelectric device, the off-resonance actuator. Use that current as a sensor. So piezos have self-sensing capabilities. It's really quite frequently utilized, the self-sensing capability of a piezo actuator, that the current can be used to tell, or even the polarization can be used to tell the displacement or the velocity. So in this case, it's not a capacitance you're dealing with. You're basically dealing with the current generation source, which has to do with the a velocity term. Now, wherever you choose to pick where that velocity exists is up to you. So it's a little more mechanical measurements are a little more user dependent, in the sense that you get to choose which point in the device you choose as a reference. Do you choose the tip? Do you choose the middle? Do you actually, like, let's say you have a tube actuator, and you have a Poisson's ratio going. Do you choose to use that Poisson's ratio as a comparison metric for the entire actuation? So you get to choose that point, and that's one reason why electrical measurements are so standard, because obviously there's only two terminals, so obviously you're going to measure voltage and current there. But for mechanical, on the mechanical side, you have to choose a point. And as long as you choose that point, you stick with it, you should be good for the most part. Let's continue. So it's multiplied by the velocity times A, which is called a force factor, but it actually allows you to convert velocity into current. And if you took velocity and you made it into displacement, you can say delta D for displacement. You can multiply that by omega to get velocity. So you can kind of have the equation in a couple of friendly ways. All right, now it's taking one step back and just understanding the off-resonance actuator. On the y-axis, we have displacement, and on the x-axis, we have force. These are the forces on the outside, and the displacement at, let's say, the edge of your actuator. So at the top, for the maximum displacement, we have, well, your piezo's capacitance, the current equals the piezo capacitance times the voltage times omega, which makes current instead of charge. However, that also equals, and you see on the bottom equation, that capacitor D, C subscript D, which is the clamped capacitance or that intrinsic dielectric capacitance, plus your A times omega times delta D. Now, what happens here is as you travel down this line, and if you have, let's say, an external force, whether that be a spring, whether it be mass loading, pushing back on the on your actuator from force equals mass times acceleration. So as that mass is getting pushed back and forth, it's causing resistance or force to be opposite. That's going to make you travel all the way down this until, if you have an infinite mass or an infinitely stiff spring in parallel with your device, you will only have your clamped capacitance. That's actually something you can't really measure directly, because you're not going to get into a situation where you are truly clamping your device. All right, let's take a look at how we can figure this thing out, how we can determine all these terms, so you can come up with a nice actuator equation, so you can measure current in your application, and you can get out your velocity and say, look, boss, we don't need to have these external sensors. We got our piezo can do it all for us. All right, so we have this multilayer actuator with a mass. Let's say it's like this, or it's like this, whatever you want. So when it oscillates, the mass is going to provide an opposing force. Assume it's low enough frequency, force equals mass times acceleration. When you start to get higher frequency, you may get other types of acoustic modes where you have nodes and antinodes, or you get that. In that case, the analysis is going to be much harder. I'm sticking to off-resonance actuators. You put on a mass that doesn't excite a resonance. That might be hard to get too, but depending on your actuator, especially if your actuator is soft, like a bender, this is going to be much easier. Now we're looking for this A factor, which is the relationship between voltage and current between velocity and current for your off-resonance actuator, depending on wherever you decide to measure velocity. So the first step in getting this is to first measure the displacement and current with and without a mass. So you have two cases, or you can measure just with two masses. Both of those are fine, but with and without a mass kind of provides an easier metric. But as an engineer myself, I would choose two sizes of masses. If those can be accommodated, that would probably make the whole system a little more dependable. Next, we're going to calculate the decrease in displacement and current. That's easy. You minus the initial state minus the final state. The final state with the mass is going to be lower, or with the heavier mass, it's going to be lower. That's easy. That's a subtraction. So this is basically what we did here. We had A equals delta current divided by delta velocity, which you could also write delta displacement. The change. This wouldn't be delta displacement. It would be delta displacement, like the change in displacement. Just so you have multiplied by omega. So you could put another delta right there. And again, the current mechanical is equal to the A factor, the force factor, which converts current into velocity into current in this way. So once you have your equation, you will be able to take your total current and go back to this equation here, where the total current is equal to the clamped capacitance times voltage multiplied by omega. You'll be able to take this equation and solve for the clamp capacitance. So you'll be all good there. So you'll have that whole thing cut out for you there. So here's a bonus. I love bonuses. Love things I don't expect that are good. So if you want, you can also use the same information to calculate the stiffness of your device. So in the first side of the equation, we just have the regular old spring constant. Nothing too confusing. Force equals the spring constant K multiplied by the change in displacement. Now, this is not the change in displacement from beginning to end. It is the change in states. So because we applied this force and we get less displacement than normal, less displacement than free displacement. So that delta between what we got with and without a mass, that's calculated. That's what we're describing on this side here. We write delta F, which is free displacement, the maximum displacement for the free displacement, and delta M, with the mass we have less. So that difference there. So that force, we know what it is. It's mass times omega squared times delta M, delta dm, which is a displacement with the mass, the total displacement with the mass, and this omega squared is just using acceleration, so force equals mass times acceleration, and that equals that same thing on the other side. You solve for K, and now you have the spring constant, and in effect, you've completely characterized your whole off-resonance actuator, and you're good to go. You have a bunch of parameters to play with, to understand, to compare, now to use intelligently in your sensor, your actuator, and you can take full use of your sensor capabilities. You're watching the Piezo SHOCK Show with your host Dr. Shakani, answering your questions on piezoelectric and ultrasonic device technology and development and analysis. Feel free to check out the description for the notes, the presentation notes, as well as a link to sign up to receive updates on these videos. It's an email list I have that sends you updates and also sends you the slides, so you can go over that before you decide to jump into the video, because we all like to be prepared for the awesomeness which is coming forward. The other thing is that I have a link as well for taking a look at my consulting offerings. So I'm a consultant. I do work for companies developing ultrasonic transducers. So if you need help in that area, if you get stuck, you know who to call. It's an obvious choice. Make the right one. All right, so see you next time, probably tomorrow, on episode number 29.